Alright, welcome everyone. Good afternoon. As usual, guys, if you have any questions from what we covered last class, which was a quick review of the basic functions that are provided for running some statistics, in particular the random number generation. Let me just double check that I'm not mute. I think you should be able to hear me by now. And see the slides. So again, if you had any questions about what we covered last class or the assignment that, as we discussed, is not due this Thursday but next week instead. So I think most of you were present last class where we kind of agreed that instead of having 6 assignments, we're going to have 5 assignments for approving the course. So what I'm thinking is, because I still would like to give you the opportunity for practicing some of the stuff that we are going to discuss in whatever is left from the course, is perhaps posting on next Tuesday what will be assignment 5, and then on Thursday, which will be not this Thursday but Thursday next week, over last lecture, posting assignment 6. And the way it will work is you will have the option to choose which assignment you would like to work to submit. You can submit both if you wish, of course, and then I will be just considering the best 5 grades for your final grade. So in principle, it's just 5 assignments, and you will have the option to select which one to submit for assignment 5 or 6. Okay. And if you want to submit both, you are welcome to do so. I will try to review them and provide the feedback as usual. So I leave open the opportunity for you guys to practice with that. And what we can do is, instead of having 1 week for you to work, you will have 2 weeks as we did with this assignment. So in that way, I think it's not as much pressure and time constraint. Okay, is that clear for everyone? Did I manage to explain more or less what I had in mind? So it will be 5 assignments for approving the course instead of 6, and then you can pick between assignment 5 and 6, and I'm going to post them. I think I was thinking of posting one on Tuesday, next Tuesday, one on Thursday, next Thursday, so you guys have time to digest, and the due date for both will be 2 weeks from next Tuesday, from next Thursday. That sounds reasonable for everyone? Let me know what you feel about that, what do you think about it? Okay, so I have a question from Dorna here about the apply. So let's go to the slides and see in particular the examples for apply. So the 2 arguments for apply are, the first argument in this case is a vector, and the second argument is a function. So what apply will do is it will take each of the elements in the vector and apply the second argument, which is the function, to each of them. So in this case, we are using the rnorm function, which is the function that will generate random samples drawn from the normal distribution. And then it will take 1, 10, 100, 1,000, and 100,000 as inputs for that function. So it will return, in the first case, one random number drawn from the normal distribution. In the second case, it will return 10 random numbers drawn from the normal distribution, and so on, right? 100, 1,000, 100,000. I'm not showing you here the example, what is going to return, but basically it will be a list with actually 5 entries. And the first entry will have 1 number, the second entry will have 10 numbers, the third entry will have 100 numbers, 1,000 numbers, and 100,000 numbers. And that's why it's useful in this case to use lapply, because it's not an homogeneous data type. Now what I'm doing after is, again, I'm applying lapply again, and now instead to this vector ns, I'm applying it to the random numbers vector that we just generated. So this is a list, and that's why I'm using lapply in this case, and then I'm using the mean function, and that is why now you only see one number per entry in the list. So the list still have 5 entries, but instead of having 1, 10, 100, 1,000, and 100,000 elements in each of the entries, you only have one because it's the mean. So it's going to collapse. It's going to compute the average of whatever numbers it is. So you can very easily see here the number that was sampled in the first case is 1.5 whatever, because there is just one number. So the mean is equal to that number. In the second case, that mean changed because there were 10 numbers. So now it's averaging the values of the 10 numbers. Third case is for 100 numbers, and so on. Okay, most of these functions work in the same way. Variations on this is apply or mapply, which basically change a little bit the order of the arguments, but in all the cases the idea is the same. You take a vector or a list or a data frame or a matrix, and then you apply a particular function. And what this helps with is to avoid the need for looping, for going through each of the elements and applying each function to that. So we discussed about this, I think, last class. It's a very elegant solution in the sense that it's very clean code. It's just basically one line of code instead of having a for loop and a body of the for loop. And on top of that, one of the best things is that in terms of performance, it's very, very good. It can be seen as some sort of vectorization. So it's highly recommended to use this method whenever it's possible. Okay, is that clear? That was the kind of what you were, the clarification that you were looking for, Dorna. Please let me know if that is more or less clear. Okay, perfect. All right. So I think we cover most of the examples with the apply functions. I mentioned this is one of the things you're going to need to use for assignment 4. And in particular, I would recommend that you use one that returns a vector, because the plot MC function that you will need to use is expecting 2 vectors. So I think someone was using lapply, and lapply, remember, returns a list. So when a list is input in plot MC, some things may not work. Okay, so just bear that in mind. So I think we cover most of the apply functions. Again, let me know if you have any questions. And we're going to go now into a very interesting part of the course, and unfortunately it's going to be really short in this course, because this course is mostly aimed to programming, but I think I mentioned this several times already. R is very well suited to deal with statistical analysis. And in particular, one of them is what we usually refer as modeling. And you can find this by different names, right? Fitting, models, regression. Depending on the field, and depending on the type of analysis, it goes by any of these names. So, but all of them are synonyms about of this. So the basic way in which people usually do this is you go and collect some data, or you have some observations coming from simulations, coming from experiments in the lab, coming from somewhere. The starting point is having some observations or some data. Then what we want is to assume or propose a given relationship between the observations that we have, and that is basically what is the model, or the function, or the relationship between your observations. And this mathematically can be explicitly given by a very theoretical background, saying, okay, my function relates x and y variables, and what I'm proposing to do is to analyze that. So basically, when we do the abstraction of the relationship between these variables is when we actually generate the model, and then what we need to do is to adjust to find the parameters that actually, the empirical parameters that describes this model. And that's the process usually, and I'm making or saying big words just to say, okay, you have some data, just fit a model to that. That's the straightforward way of saying this or doing this. And And that straightforward way of saying things sometimes hides some things, like what is the method behind. And usually the method that we use, and the method I'm going to show you today, is ordinary regression. But there are other methods. Now, another thing that sometimes escapes us, and this is a very important part, and unfortunately, unless that you say something differently, so we still have some room, I think, to play with at least one lecture, but unless that you say something differently, the part I'm going to skip, but is truly important, in particular when you are doing research on this area, and in particular when you are publishing results coming from models, is how you test, how you evaluate, and how you analyze your results. Okay, so that part, and I have a few topics at the end of this batch of slides. The idea for today is to cover this and perhaps start in the visualization part that you probably saw the slides already in the class. But this part so far right now is not part of this, but this is crucial. Okay, this is as important as the creation of the model itself, the part where we actually measure, where we try to understand how good, how much trust we can put in our model. Okay, and as I mentioned, depending on the field, this process is called modeling, fitting, regression, etc. Probably most of you are familiar with this. So let me know if this is like too redundant or going too basic or too slow. So the first we're going to start is with our old friend. Our first approach, if it was a physics course, I will say the zero order approximation in a Taylor expansion is the linear model. This is like the harmonic oscillator for any kind of problem in physics. It's the most basic approach that you can take to your data. And basically says that if you have two variables, y and x, there is a relationship between y and x, y being what is sometimes called the response, and this is the causing variable, and then a and b are parameters. Now, this, I have to tell you, is already an idealized version of any model, in particular for real data. And the reason for that is that we are always in presence of something called noise or variation in the data, something that is intrinsic to the method in which we are actually capturing or collecting the data, and that we cannot control. So that is something to bear in mind. That's something that, depending again how deep one goes into the statistical field of analyzing models, will play a really important role. But that's something to bear in mind. Okay, we basically, again, these kind of things we basically neglect or disregard when we do our analysis. But in some parts, in some areas, it's quite important and quite relevant. I would say it's something that one needs to bear or keep in the back of one's head, because sometimes these terms start to dominate and affect in a very important manner the results of the conclusions that we can draw from our models. So for visualizing or for exemplifying a particular case, we're going to take, for instance, a very simple model for plant growth rate, and we're going to say that the growth rate can be given by different factors or variables. That's another way to say this. It can be the amount of water that we provide to the plant, the temperature, the fertilizer, if there are insects or not present. So different things, right? And again, this is already a quite complicated model, so I'm going to still simplify this a little bit for the sake of showing you how to create a model in R. So let's say that we are going to use the trees data frame that R already has incorporated. So there is, if you look at the data function, there is trees, and so trees actually, if you look at the trees data frame, it has three variables: girth, height, and volume, and it has several observations. Okay, so the first thing I usually recommend to do when one wants to create a model is to try to visually inspect how the data looks like. And because this is quite relevant many times, R already brings some functionalities for doing so. It turns out that if you had the data placed in a data frame format, you can just use the plot function and the name of the data frame, and R will basically allocate each variable in a kind of mosaic plot. This is another way to generate this type of plot using the mosaic function. But if it is a data frame, you can just already do plots, the name of the data frame. And here, for instance, girth, which is the first column, is represented in the horizontal axis in this vertical thing, and then in the horizontal axis in the horizontal axis in the first row, in the first column, and the vertical axis in the first row. So here, for instance, if you look at this combination, this is girth versus height, or here this is girth versus volume. So you basically draw the line between the variable and the next variable, and that's the plot that you get. Okay. So for instance, by looking at this type of plot between all possible variables in the data frame, I can very clearly see if there is any particular trend between the variables, any particular relationship that is clearly or remarkable between the variables. And for instance, in this case, it's quite remarkable that girth and volume, so if I could do girth and volume here, the relationship appears to be quite linear. Okay, so now if I want to explore that plot, that inset a little bit more, what I can do is plot, and then I'm going to put, in this case, trees in the x-axis. So this is my trees girth in the x-axis. So this is my horizontal axis, and that's the first entry here. And then comma, whatever goes in the vertical axis, in my y-axis, if you wish. So in this case, volume. So trees volume is the variable in the y-axis. And you can see it's more or less what you see here as well. Okay, so this may be a hint that just by looking at this data set, you can, by visually inspecting the data set, you can start to draw some relationships or start to imagine some models that describes the relationship between these variables. Okay, any questions about this so far? Okay, so given that by inspecting the data, by visually looking at the data, or because you already have in place a model in your mind that you would like to explore, now let's say that we want to draw or create a model, a relationship, a functional form, that's another way to say this, that relates the girth of the trees with the volume of the tree. Okay, so how we will do that in R? Well, there is a function called linear model, or LM, that allows you to do that. So here I'm going to use the ln function. I'm going to put here my y variable, and notice this tilde notation. This is an operator that says whatever is on the left has a relationship or is given by whatever expression you put on the right of that operator. This, by the way, is known as a formula notation. That's a very common thing in R, to have formulas notation, and whenever you have this tilde operator, that means the thing on the left of the tilde operator is given by an expression prescribed on the right of that operator. In this case, it's a very simple expression because we are dealing with just a linear model. We are going to see by the end of today how to do a quadratic model or any more general expression, but that is the way that you will write a formula, a potential model, a tentative model for the data. So my y variable here, tilde operator, relationship given by my independent variables, if you wish. Now, when you do that, when you do a linear model of the expression, I will return this information to you. It will say, okay, the linear model function was called with, and identifies exactly that whatever you brought here is the formula. And then what it gives you is just the coefficients for the formula. So in other words, this is trying to say my expression for the volume of the tree is a constant multiplied by the girth of the tree plus another constant. And this is because it's just a linear model. It's the expression of a line, a straight line. So this means that by looking at these results with this data, the volume of the tree is given by this constant, a negative constant, plus a positive constant multiplied by the girth. Okay, so basically, and this is another way you can rephrase this. So it's the same model that we are creating, just the variables names and where the data is coming from. So instead of writing trees, $volume, trees, $girls, you do volume tilde girls, and then you specify that the data comes from the trees data frame. Okay, so another way to do that. Any questions about this? As you can see, it's very easy to actually create or do a model in R, given that you have the data, of course, and given that you have an idea of what kind of functional relationship you want to propose. The other thing I wanted to mention, and I'm not going to mention much here again because it's a very high-level view of this, is the underlying method that the L function is using is ordinary regression. And or to be more specific, ordinary least square regression. What it does is for each data point, given that you get the formula of the model, it tries to minimize the distance between the shape, the line in this case, of the model and the data. And it does that by looking at the difference of the separation square. By doing that, by trying to minimize that, is how it finds the coefficients, in this case the independent coefficient or the coefficient in front of the linear term of the model. Okay, just to give you a little bit of what the LM function is doing underneath. Now, a better way to do this, instead of just executing LM volume, is to assign this to a variable, and I'm using the variable m here, not really good name, but that stands for model. So I'm going to assign my model, the result of using the LM function, to a variable called m. And then I can inspect m, and basically I get the same information I was getting in the screen. Okay. Now, because I assign the result of the LM function to a variable, I can do more things as well. For instance, I can now start to ask the question, okay, what are the coefficients of this model? And because, again, this is a linear model, I will have only two coefficients. The linear coefficient in front of the girls, so this will be the slope of the model in this case because it's a straight line, and the independent coefficient or the intercept. Okay? Any questions about this? Just checking that the chat is clean. Okay, so sorry Laura, I didn't see your question again before. So the question from Laura says, does R assume the function is linear because of the way the LM statement is written, or because linear fits the data best? Really good question, Laura. No, it does two things. So it doesn't. So R, differently than other programs like SAS or Stata or any other program that may be able to run fits for you, doesn't assume anything. You have to specify. So there are two pieces here. The first piece is the relationship I'm indicating here is the one that is saying volume is linearly related to girth. And I'm going to show you in a few more slides how to create a quadratic relationship. Okay, that's one piece of information. So you are basically in charge of specifying what is the relationship that we want to fit. The second part of the question is related to what you mentioned. What happened if the data was exponential? You can still use LM, but then we open kind of a Pandora box, okay? So you can use LM. So the LM function will work with any kind of data and with any expression that you adjust here. So let's say that your data is exponential. Usual trick, I'm not saying it's the best because it has some downsides to it, is to linearize the data by taking the log of the data, okay? So if I have exponential relationship, basically your data will grow as an exponential. I can take the log or semi-log of the data, and then my relationship will be linear. So I can still use an expression like LM with a linear model. I could do LM with an exponential as well. But one thing to bear in mind, and this is where things get really interesting in terms of data analysis, is how the errors in my fit distribute. So the LM function, because it's using the ordinary linear regression methods, are well suited for when your errors are distributed normally. If by any chance your errors are not distributed normally or any other things fail, like the variance of the errors is not constant, the LM function is not the best candidate for you. And instead of creating a linear model with the LM function, you need to use something called a generalized linear model, which has a function, it's called GLM, for generalized linear model. Many people confuse that when you don't have a linear expression that you need to go to the generalized linear model. That's not correct. It's when several of the assumptions, or at least one of the assumptions that we are using to create our model fails, is when you need to migrate your models to a generalized linear model. And it can be even the case when you have a linear relationship, but the distribution of the residuals or other indicators that tells you how good the model is are failing. You already need to go to a generalized linear model. And it's because the assumptions underlying the statistical description of the model is failing. And it's not necessarily because of the form or the relationship in the data. So it's a really, really interesting question. I'm just scratching the surface here. So as I say, I usually spend like several lectures talking about this. But for the reasons I have mentioned already, we don't have enough time. So again, if you guys are interested in this, I will be happy to have a one lecture just focusing in regression or model diagnostics, as the other name, or generalized linear models. Okay. Let me know where many of us in the class, so we will have to evaluate how many of you are interested on that. But if you guys are interested, please let me know and we can try to accommodate something. Okay, I hope that I answered more or less your question. So just to sum up, the LM function works with any analytical expression or any formal expression or relationship that you want to propose. But if some of the assumptions under the model generation of the LM function fails, then you need to go to something else. Okay, and you can even use LM with exponential variables or exponential relationships. Okay, let me know if that is clear. In the meanwhile, let me show you a very, very handcrafted way for saying, for trying something at first glance, or how to predict a particular value given that we have constructed this model. Okay, I know the coefficients of the model, so now I can evaluate the model and say, okay, if I had a tree with a given girth, now the volume should be this. That's the prediction part of the model. So let's say that I had a tree with a girth of 15.12, and this is a very known standard way of predicting, but I want to show you something. So I show you what the coefficients of the model are, and are these two numbers, right? You can think about this as a vector, where the first element in the vector has the independent or constant coefficient in the formula. The second has the higher degree, in this case the linear order or the linear term. And if it was a quadratic, it will have the second, and if it was a cubic, it will have the third, and so on, right? So what I'm going to use here, if you remember from our matrix lecture, I'm going to use the inner product or the dot product operator. And to multiply this, I'm going to create a vector which has a 1 in the first element, and then the number I want to use to evaluate the model in the second. And the reasoning here is because the coefficients of the model are organized or are structured in this way. This is the independent term. So if you think about the equation that we are going to use here, it's going to have y being, in this case, the volume, right, equal to the slope multiplied by the girth plus the independent term. Now, the independent term is the first term in my vector of coefficients, and that's why I multiply that by 1. My second term is the slope of the linear term in the line, so that's why I multiply this by what is my x value, in this case 15.12. And then the inner product or the dot product, what does is basically it adds each of these products, and that's my prediction, 39.65229. So that's the predicted volume, assuming that our relationship with the data is linear, for a tree with a girth of 15.12. Okay, any questions about this? Okay, just one more thing, just to convince yourself and try to see what this operation is doing. Try to see what coefficient of m inner product or dot product with the vector 1, 0 gives you, and coefficient of m inner product with the vector 0, 1 gives you. Each of them will recover each of these coefficients, and this is just to show you how the inner product operator works and how the coefficients are laid down in this model. Okay, it's like you are projecting into each of the components basically of the linear. Okay, any questions about this, please let me know. Laura, also let me know if my explanation for your question was okay too, okay? Perfect. So one more thing that is very useful of assigning the model to a variable is it turns out that the LM function returns a very rich object. It's an actual model object, that is how it's called. And you can use the summary function on it. So when you use summary, it gives you a lot of information. It gives you, of course, the formula that we used to create, but also it gives you the residuals. So let me tell you a little bit very quickly about the residuals. So the residuals are a way to evaluate how well the model is with respect to the data. So basically, and I'm going to show you a plot in the next slide, but I'm going to, so you know what, let me show you this plot very quickly here. So this is our data. The circles represent our data. The line represents the model that we created, and I show you how to create this plot in a second, but I just want to use as an aid for explaining what the residuals are. So the residuals are the distance between the data and the model. So take, for instance, the third point here. So this third point, and I can compute the distance to the model as how far this point is from the model itself, or this other point, or this other point, or any of the points. So for each point, for each data point, I can compute the distance to the model. Okay, and that's the residual. So in principle, I will have as many residuals as data points as I have. Okay. Probably you guys are familiar with this. I just try to be sure that everyone is on the same page. So when you ask for the summary, the model also gives you information about the residuals, and it gives you information about the distribution of the residuals. And this is important again because depending on the residual distributions, we have very insightful information if the method that we use to create the model, in this case the LM function, is the appropriate or not. This is not enough. This is just a very quick view of the residuals. And again, one will go deeper into the structure of the residuals and how the residuals are distributed to learn about how well is the model, how robust is the model. Okay. The other thing it gives you is the coefficients. Okay, we have intercept, we have girth, the estimated value, the standard error, different operators. That is your p-value, by the way. And in this case, it's telling you that these values have been determined with very highly statistical confidence. So these values are way less than the traditional 5% certainty level given to the p-value. So these stars also represent how significant is the determination of this. Okay, it gives you an overall value of the R-squared value, of the adjusted R-squared, that are also indicators of how well the model performs, and you can use this to compare with other models that you want to create, and a total residual estimate of the error and degrees of freedom. Okay, so it gives you a very nice picture that one should take a look at in general to see how our model creation works. Okay, let's see if we have some questions. Sometimes the chat doesn't pop up for me, so just want to double check. So I showed you this plot just a second ago. So this is how we will visualize the model. So we saw this way to plot the data. So in this way we actually can plot these circles. But then with AB line we can actually add the model. And actually drawing a linear model is very easy because AB line takes basically the M, which is the model, and just draw the line. But AB line works is in different ways, in different modes, if you wish. So it allows you to basically pass two numbers, in this case the slope and independent term, and basically draw a line like that. Okay, we are going to see these functions in the second part, or maybe next class, which are more detailed how to draw and visualize things. But in this way we can actually look at the data, look at the model that we created using the LM function, and say, okay, this is not so bad. But what about, or we may wonder, can we do better with this data? Can I take, so these points here that are conglomerated, in particular this one or this one right here, are far away from the model. Can I have a model that basically tries to go over all these points? That's kind of the question one will ask. And say, okay, for simplicity's sake, again, let's try to fit a quadratic model. So basically, we will have a quadratic contribution and a linear contribution, right? And in this case, my equation, my model will look a little bit like this. So this is the new term here. This one is the previous part. So the coefficient multiplying the girls plus a constant was my linear model. Now I'm saying, okay, what about if there is a quadratic contribution of the girls? Can I include that in my model? Okay, and again, I'm going to show you a way to do this, like in a very step-by-step manner. Let's put it that way. There are more straightforward ways of doing this, and I will comment at the end. But I want to be sure that everyone is at least understanding what is going on here and why we have this expression and what terms we should add to the expression of the LM function. So the first thing I'm going to do is I'm going to define an auxiliary variable called girth2, so that I take the girth and I use the hat operator, so I get the power of 2 of the values of the girth. So now I can construct my model 2, M2, as calling again the linear model function LM, and this may come back to Laura's question about what kind of expression I can use, and you can see here I'm using a quadratic formula, a quadratic expression, and I'm still using the LM function. My dependent variable or predicted variable y is still volume. My formula changes slightly because now I have girth plus girth squared. Okay, and the reason why I define this is because R won't allow me to put girth tilde 2 here. Okay, so I had to define this as this variable. And then my data comes from the trees data frame. Okay, so the only thing I change is now I add a quadratic contribution to the model. Okay, all right. So if I do that now and I decide to look, so you can do the summary of the model M2, which I invite you to do, or I look at the coefficients. Now I can see, okay, this is my intercept value, this is the slope of, in this case is a parabolic shape, so of the parabola, and this is the term in front of the quadratic term, and you can see that. Now I invite you to try this if you are following the example, or if you want to decide to follow the example later on. If you do plot, and notice this is an important part, it's a subtle point, but if remember the plot function that we used to plot the points, if you do plot M2 is the model, this will generate a sequence of plots, and again, these plots are related to how we determine if a model is good enough. So it will give you a lot of these things, of visual representation of these things I have been mentioning, like the residuals, the confidence intervals, the distribution of the residuals, and again, it's something that one should look at. That's why I'm including this here. Okay, it give you 4 or 5 plots telling you about the health and robustness of the model that we just created. And you can do the same with the M variable that has the linear model for us. Okay, now let's go back and try to plot, to generate this plot here, which has the original data, the linear model, and the quadratic plot. So we saw that for generating the plot with the data and the linear model, these two commands, these two functions were good enough. Now the trickiness with any model that is higher order than 1 is that there is no function that will basically take your model and boom, plot it. Okay, so we will have to do something similar as what we did when I was evaluating the model, the linear model. So, but the first thing I'm going to do is I'm going to define a series of values so that I can actually use a very regular grid in my x-axis. So xx is going to be a vector that I'm going to generate using seek, remember the seek command, from the minimum value of the girls up to the maximum value of the girls with as many points as the girl has. Okay? By the way, the seek command is going to be useful when you create the vector for assignment 4. It's probably the one that you want to look at. So this will generate a grid, a series of values of S going from the minimum of the girls up to the maximum of the girls with as many points as data points are in the girls command. Of course, you can set this value to whatever you want. You can set it to 200, 1000, and you will have so many match points here. Okay? But the idea is just to have a regular grid here, because what I'm going to do with this is I'm going to evaluate my model. How I do that? In the same manner I showed you before. But now, because the model has 3 coefficients, I need to provide a vector with 3 terms. The first term, which multiplies the coefficient, the independent coefficient, is still 1. The second one is the one that gives you this term, the linear term. And the third one is the one that gives you the quadratic term. And that's why we have x to the power of 2. Then we have the inner product operator, and then multiply that. And this is another way to obtain the coefficients of the model 2. You can do coef, as we did here, of model 2, or just say from model 2, like in a data frame, use the $sign operator, coef. Okay, it's exactly the same thing. All right, that is assigned to a new variable yy, and instead of using AB line for a straight line, I'm going to use the lines command, which for what I had to provide the x and y coordinates, and then I'm giving here some graphical parameters. The width of the line to be twice as the usual one, and the color of the line to be in red, and that's why you see this red line here. Okay? These few commands, these 3 lines of functions, will generate that red line, and now you can see in the plot the original data in circles, the linear straight line in black, and then this piece of the parabola in red for our quadratic model. Okay? Any questions about this? Let's see how the chat is going. Okay. This is an alternative way. So I show you how to generate this red line. Alternately, I could do this. So, or you do this part here, or you do this second part here. You don't need to do twice. So both will generate slightly different representations of the model in this plot. But here, ym2 is nothing else than, again, the coefficients of the model, inner product, and what the difference here is that instead of generating this auxiliary grid of x values from the minimum up to the maximum, what I'm doing here is I'm using directly the values of the data. So for each value of the data, then I'm going to evaluate the model and see where the model falls. What is the disadvantage of this? Well, the advantage is I don't need to create this auxiliary xx variable. The disadvantage is that if my points are not more or less uniformly distributed, my representation of the model may look a little bit kinky. Okay? But other than that, in this case, it's good enough. You won't be able to notice much differences. This maybe is a shorter way of generating the visual representation. So again, you either do this for plotting the quadratic model or this second part here. Okay? Any questions about this? And let me go to the chat, because as I say, sometimes it blinks, sometimes it doesn't. So it looks like it's clear now. Okay, you let me know if you had any questions. Maybe this is too basic again. Let me know as well if you guys already knew all this, so I can move a little bit faster or to more interesting stuff. Now, I always keep this slide here for a quite important reason. And again, this is more thinking about the context of when you will do that and how to digest information provided for the models. So it turns out that when we are trying to understand relationship between variables, there are 2 important concepts here, correlation and covariance. And I have the mathematical definitions here. I won't go through this because, again, this is not necessarily a statistics course, but these are statistical driven and important concepts. But one thing I want to notice is the correlation will tell you about and let me go back to the plot I showed you before, it will tell you about how the data is correlated, how the data basically relates, but relates to a linear model. Okay, so I could compute the correlation of these data points, and that will give me some information about how the data will fit a linear model. Now, the reason why I keep this is because this tiny plot, this tiny plot here on the left, this is called the Anscombe quartet. What you're seeing here are 4 different sets of data points. Each of these data points has the same correlation coefficient, has a correlation coefficient of 0.82 roughly. Okay, all these 4 data sets, this one right here, this one right here, this one right here, and this one right here. You compute the correlation coefficients, each of them give you 0.82. The reason why I bring this up is most of the people will compute correlation coefficients and say 0.82, linear model, let's go. And that's your result. My point here is look always at the data. This may be a relationship where a linear model will be good enough, although I will say there is some dispersion in the data. This clearly is not a linear relationship, it's more like a parabolic relationship, no doubt about it. This may be a linear relationship, but this is what we probably will identify as a outlier. And this is something similar to that, but with a very, very kind of no functional relationship other than a vertical line. So the message here is, even when you can, and I show you in a second how to compute the correlation coefficients, always bear in mind looking, inspecting visually at the data, because you may find surprises there. Okay? So how you compute correlation, covariance, and variance in R? Well, there are 3 functions for it, core, cov, and bar. And it's very easy. You just use your x and y variables, and that's it. So 3 squares, 3 volume, that give you a very high correlation coefficient. So there is no doubt here the relationship is almost linear, I will say. Covariance will give you the variation between these 2 variables. The variance will give you the variation again between these 2 variables, or for each variable independent. Okay, you can also compute the standard deviation, which is nothing else. You remember the definition, that the square root of the variance, and we can actually kind of mathematically prove this. So if I take the square root of the variance of the girls and then the standard deviation, this should be the same, and it is. I'm using the equal operator here to compare these 2 values. Okay, there are more things that the correlation function can do, so you can look at the help or question mark core, and you will see that what is happening underneath is that there is some sort of correlation test, and there are many parameters that you can play with. Okay, again, I just wanted to mention this because I think it's something important to bear in mind when one is doing or creating models, to see how the data behave and how it compares to the model. Okay, any questions about this? Let me see again, sorry, wrong button. Let me see again the chat. Okay, so one final comment, and this is the things that I'm not going to discuss. So this is my last slide for models, for statistical models or generation of models in R. But some things I already mentioned when I answered Laura, and some things I would like to take a few minutes to mention. Big topic that we are missing, and I will be happy to include it in a lecture or less than a lecture if we have the time, is what we call model diagnostics and model validation. So far we created the model, we were able to inspect the model with respect to the data, but we haven't said much more about, is this model valid? Is this model correct? Can we with which certainty, with which confidence we can claim this model is good? The method that we have used, the method that the LM function uses is, as I say, is ordinary linear regression. Okay, so we can spend a whole lecture talking about regression and more general models, so like the CLM, as I mentioned before. Other big point or big topic in statistical analysis is hypothesis testing or statistical tests. So that is a huge topic as well. We are not going to say anything about that. Related to some corollary or applications that one can use from that is power analysis. And then topics related to machine learning, like PCA, cluster analysis. Again, I'm inclined, depending on how I was thinking, and I may have time today for doing more about visualization, but apparently we didn't. I talked too much. I apologize about that. We may be able to have a lecture on machine learning, but if we have one on that, we won't be able to have something on model diagnostics. So again, if you have any preferences, I will please urge you to let me know. Monte Carlo techniques is a whole topic. You can take a whole course in Monte Carlo techniques. I just show you a little bit, give you a little bit of flavor of it in the assignment. But it's a humongous and very important technique and topic. And then statistical paradoxes. The example of the Anscombe quartet is just one of them, while there are many others that allow you to not allow you, but urge you to be careful with the results that you draw from statistical analysis. And I will be happy to discuss many others, but one is something that one should be careful. Okay? So let me know if you are interested in any of the things. Again, we can see there is not much room. We have only 3 lectures left, so there is not much room for us to play with. But if I have the chance, I can move things around. I'm taking Dorna's question right now, but just to let you know, my plan for the rest of the lectures are, well, I was going to talk a little bit about plotting today. Maybe we still have 10 minutes, so I may be able to do so. But for sure next class, and then we have 2 lectures left. I was thinking of covering some machine learning techniques like clusterization or classification algorithms, and then doing high performance R at the end. So it's a series of recipes and prescriptions that you can follow when you are reaching the limit of the performance of your computer, and what kind of things you can do for running a supercomputing using R. That's not the most typical case you will see, but it's more common than what you will expect. So again, that was the idea I have in mind. Depending on how things go, we can accommodate a little bit. There is not too much room, but definitely we can do that. So I think Dorna has a question and a comment, so I will take both. And again, while I'm doing that, please feel free to express whatever you are thinking of. So what's the difference between variance and covariance? Okay, good question. So the variance applies to a particular variable. Okay, so if I have, let me see if I can show you the example. So here, for instance, you are seeing variance of the girth, meaning the x value or the y value, right? And that tells you basically how dispersed the data is in the x-axis or in the y-axis, kind of. Covariance is a measure of how dispersed is the data in both quantities. And something to notice here is when you look at the covariance. So formally or mathematically speaking, a covariance is relating 2 variables x and y. But R, when you ask for the variance of x and y, is exactly the same. So mathematically and formally speaking, variance of 2 variables is the same as covariance of these 2 variables, because it takes into consideration the variation of each variables and combine them together. Variance, explicitly speaking or formally speaking, is just for one variable. So it's how much dispersion is in the x variable or in the y variable, while covariance is how much dispersion is in both of them at the same time. Okay? Let me see your second comment. You also did a little more into plotting graph. Absolutely, I had a whole lecture. The slides are actually posted on the website, so we're going to spend at least one and a half lectures, maybe 2. If you guys are interested, visualization and plotting is something that I really like, and I'm really excited to showing you a couple of packages, at least one package that I really like it, which is Plotly. I don't know how many of you have heard about Plotly, but Plotly allows you to do interactive visualizations, and it works in R, Python, and many other languages. It's an open source project. It's a Canadian project, by the way, so it's a very interesting package, I would say. Okay, so that's, yeah, for sure we are going to do way more in plotting. I just use a few commands today, with the excuse of visualizing the results that we were getting, but that's the next topic actually. Okay, I have 5 more minutes, so maybe if you guys don't have any questions, if not, please feel free to ask. I will quickly go into, I have it somewhere, there we go, my visualization slides. And as you can see, there are a lot of them. Let me double check again that we don't have any questions in the chat. I'm sorry. As you can notice in my slides, you can click on these buttons here and take you to the slides. But in this case, I just wanted to double check that we don't have any questions. Okay. Okay. So that's the beginning. At least we will have 5 minutes, and that's some time. So the plan for the visualization and plotting lecture will be to cover, and it was going to be more than one lecture, so lectures actually, the basics of visualization in R, how to create professional plots. So this is, I believe, is an important part, and I think this is going to be one of the assignments. I usually have an assignment about creating scripts to generate professional plots, meaning plots that should be publication quality, and usually they require to create functions, and we will see that. Advanced plotting techniques, animations, especially if you guys are generating data that can be put in a sequence of frames, and then the interactive plotting with Plotly. Okay, so it's a little list of topics, but I think it's worth it, and I really like this topic. So, but again, let me know if you guys think that it's not worth it. So far, I think Dorna was keen to this. So let me start with the plot command. We saw the plot command just a few minutes ago, and what I'm going to do here is I'm going to generate a vector x that goes from 1 to 100 and then is divided by 100. And basically what this will do is give you a uniform vector with 100 values from 0 to 1, right, or 0.1 to 1. And then what I'm going to do is just use the plot command, and then I'm going to use a mathematical function, a sinusoidal function, which is going to take x multiplied by 4 multiplied by pi, and basically give you this very beautiful sinusoidal shape. So in this case, differently than before, I'm just using plot with only one argument, the sinusoidal function. And what you can see here, because my vector x has 100 elements, is that it plots the value of the sinusoidal. You can actually see the function here on the y-axis, and then uses as the x-axis the index of the vector. And that's why it goes from 0 to 100, because it's using, because there is only one argument, the index as the x position here. Now, if you want to be more accurate and say, no, use x as the x-axis, then you do plot x, comma, sine of whatever. And that is the way that we were doing before, x, comma, y. So what comes after the comma is what is represented in the y-axis. Okay? No surprises here. I'm changing just, instead of using the data, I'm using x and a mathematical expression for a function. Now I can change things a little bit. The default behavior is to draw the axis, a square around them, canvas if you wish, use the circles. So there are a lot of arguments for the plot function. So here I'm plotting the same data, but now I'm saying type O. That's why it says to put circles or tiny dots. And then the color equal blue. I showed you before that you can enumerate colors with numbers, but strings also work, so blue as a string will work. And axis equal false. Basically, don't draw the axis in the plot. Okay, I can now use our function lines from, again, a few slides ago, saying, okay, use x as x, but now change and do a sinusoidal with twice the period. So now instead of using sine x 4 pi, I will do sine x 2 pi. And that's the red line that you see there, because now I'm specifying the color to be red. Okay, one more thing to notice is the plot function by default creates a new plot every time that you execute, and that's what you were seeing before. My first plot, second plot, third plot, and then my fourth plot is adding a line. So lines add on top of a previous plot, while plot by default creates a new plot. Okay? One more thing, if I want to add the axes here, I can say title x label equal times in second, for instance, and that will add a x title here. I could do the same with y label and put something else here. Otherwise, by default, you will put the name of the function that we use in plot. Right? Any questions about this? Okay. We're almost at the hour, so let me just. I think this is more or less what I commented before. If one of the arguments is specified, plot will plot basically against the value index. The default for every plot is to create a new plot, meaning that it will override the previous one. But there is a command that you can use, par new equal true, that will allow you to aggregate plots. Okay, so if you want to keep adding plots and not overwriting them, you need to use the command par new equal true. Alternatively, you can use the lines command, which adds on top of this. If you want to customize access, you can say annotation equal false, and then you can take control of basically putting whatever you want in the access. We are going to see how to create new windows with device new and device set. So that's something that will come. A couple more of comments. So par new equal true, as I saw, will allow you to keep adding things instead of overwriting. You can specify the fonts of the plots by saying family equal and the particular type font. Similarly, you can specify the characteristics of the font if you want to have default or italic or bold and so on. Par annotation equal false, do not annotate the plot. And then this is the way that you will create insets or subplots. Par mf row. So you will notice par is one of these super powerful functions, in particular for customizing the plots. And we're going to deep into this. So for instance, if we do part mar and this vector with 4 values, it basically allows us to control the margins of the plot. And something that you may notice here, for instance, is that when it generates a plot, there is a lot of white spaces that are basically wasted. So part of the professional plotting part is going to control those white spaces. Okay, I think I'm done with my comments. I will retake here on next class because we are over a little bit. I think Richard has a question or a comment. And the question, I think it takes radians. Okay, so I think the arguments for the sinusoidal functions, either sine, cosine, tangent, and so on, are radians instead of degrees. That's the default usually in many of these functions. But you know what? The best thing will be to check with help. But I will bet that it's taking radians instead of degrees, for instance. Okay. If you guys don't have any more questions, I think we're going to stop here today. As usual, I'm going to stay in the chat for a few more minutes. Let me know if you guys have any questions from what we covered today, or the assignment, or anything else, okay? Or if you have any particular interest or any particular topic that is of your interest from the ones I mentioned. Otherwise, if I don't hear much from you guys, otherwise the plan will be, okay, this week cover visualization. We may need to go over next week a little bit with visualization because I'm a little bit late with my itinerary. And then the last class could be, well, it could be in principle I was thinking to do high performance R, but it could be machine learning, or it can be model diagnostics. I would really like to hear from you if you have any particular interest. Okay.